This is lecture 4D for Calculus 1 on L'Hopital's rule. L'Hopital's rule is a very important rule, and by the way, it's pronounced L'Hopital's rule, not La Hospital rule. So L'Hopital's rule. Okay, and it operates on indeterminate forms. If you were taking the limit law for f over g right here, the limit law says take the limit of f and divide by the limit of g, as long as the limit of g is not equal to 0. So if the limit of g is 0, then we've got a problem. Sometimes we could use algebra and simplify and rearrange this fraction and eliminate that problem, but other times we can't. L'Hopital's rule applies to the special case when the limit of g would be 0 and at the same time the limit of f is 0. Such situations are called indeterminate forms. Okay. Right. So there are several kinds of indeterminate forms or types. There's the type 0, 0. That means that the limit would go to 0. Here, if I take the limit as x goes to minus 1, the numerator would go to 0, the denominator would go to 0. Here, if I take the limit as x goes to 1, the numerator goes to 0, and the denominator goes to 0. There's another indeterminate form of the type infinity over infinity. In this case, I'm going to let x go to infinity. The exponential in the numerator would go to infinity, so would the denominator x cubed. Those are two forms that you know so far. Indeterminate form of type 0, 0 and infinity over infinity. L'Hopital's rule says that if you have that situation where in taking a limit of f over g, both limits would go to 0, then you can compute the limit by taking the limit of the first derivatives of f and g. Now this applies only when the limits of f and g are both either going to 0 or infinity. F and g have to be differentiable. And the limit of g prime cannot be 0. If it is 0, that's okay if f prime is also going to 0, and then you have another 0 over 0 indeterminate form. In that case, you can just apply L'Hopital's rule again and take the second derivatives. So I have to tell you what L'Hopital's rule is not. It is not the rule for finding the derivative of f over g. It's a rule for taking the limit. If you want to take the derivative of f over g, you have to use the quotient rule, or you have to use the product rule in the form of the chain rule. But you do not use L'Hopital's rule. So here is an intuitive idea, not a proof, but an intuitive idea of L'Hopital's rule. Let's say you have the function f at x and you consider some linear approximation to it. So if you have f at x would be approximately equal to f at the point x naught plus the first derivative times x minus x naught. That's just the equation for the tangent line. Here's the same thing for g. G of x is approximated here by the line that is tangent to it at x naught. Now what if I put this fraction f over g, and I'll approximate the numerator by x over x naught, and the denominator, I'm going to approximate the numerator by the linear approximation of f, the denominator by the linear approximation of f. Okay. Now because they're both 0, I know that this is going to go to 0. Whoops, can't do it. Okay, so just cross it off. G of x is going to 0. Those are gone. So I end up with f prime at x naught times x minus x naught, g prime at x naught times x minus x naught. So I'll just go ahead and, whoops. So I can just cancel those. And I end up with f prime at x naught over g prime at x naught. That is a very crude way to think about it. What you're saying is that it's the first derivative at a place where both f and g are 0. So when you get done canceling everything, you just end up with the first derivative at 0 over the first derivative of g at 0. Now I'm going to prove, this is a proof of L'Hopital's rule for continuous functions. Instead of starting with f and g, I'm going to start with f prime over g prime. So I'm going to take the limit of f prime over g prime as x goes to x naught. Well, what is f prime. It's f of x minus f at x naught divided by x minus x naught. Here. Same thing here for g. Okay, instead of using the difference quotient written as x and then x plus h, I'm using it as x naught and x. It's the same thing. All right, but I need this terminology. Okay, so what can happen here? Right, some things can cancel, obviously. These are going to cancel. Well, I'll write them over here. These are going to cancel. And since I'm taking the limit of both, I could work that backwards and get the limit out of there and get it out in front. Right. So now I have the limit of f at x minus f at x naught, g of x minus g at x naught. But I said that they were both 0 at x naught, so this is 0 and this is 0. I end up with the limit as x goes to x naught of f over g. So in the proof of L'Hopital's rule, you don't start with the limit of the f over g and proceed to the limit of f prime over g prime. Instead, you start with the limit of f prime over g prime and end up and go the other direction and end up with the limit of f over g. Very important, and you will use this in the future. Okay, I want to take the limit as x goes to minus 2 of a numerator, which is x plus 2, and a denominator, which is x squared plus 3x plus 2. When x is minus 2, both of these are polynomials. To complete the limit, all you have to do is evaluate them, and when you evaluate them, you end up with 0 over 0. So because it's of the indeterminate form 0 over 0, I can apply L'Hopital's rule. So what I do is I take the limit of the derivative. What's the derivative of x plus 2? Well, it's just 1. What's the derivative of x squared plus 3x plus 2? It is 2x plus 3. Now I can take the limit, letting x go to minus 2 and end up with minus 1. Who would have guessed? All right? It's pretty interesting. You would not have thought that when you're taking the limit of two things, both of them going to 0, that the limit would be minus 1. Here's another example. I'm going to let x go to 0. If x goes to 0, this exponential goes to 1, and this numerator goes to 0. And of course, the denominator is going to 0. So I'll apply L'Hopital's rule because this is of the type 0 over 0. I take the derivative of the numerator. Well, the derivative of minus 1 is 0. The derivative of e to the 3x is 3e to the 3x. Okay. What's the derivative of x? It's 1. Now let x go to 0 and I end up with 3. We can do the same thing when we have the indeterminate form of the type infinity over infinity. Here I'm going to take the limit as, oops, I lost my pointer, as x goes to infinity. The log of x is going to infinity. It blows up slowly, but it blows up. And x itself will go to infinity. So now let me apply L'Hopital's rule and take both derivatives. The derivative of x is 1. The derivative of the natural log of x is 1 over x. All right? So if I let x go to infinity, I end up with 0. So instead of this infinity over infinity, I end up with 0. That's interesting. All right, here's another one. The numerator is going to 0. The denominators, they're both going to infinity. So I take the derivatives. The derivative of x is 1. The derivative of x, e to the 3x, is 3e to the x. And now, if I take the limit, I just am taking the limit of 3e to the 3x as x goes to infinity, and I end up with infinity. If this function looks familiar, this f of g, we did it up here when x was going to 0. When x was going to 0, this thing went to 3. When x goes to infinity, this thing does go to infinity. It does blow up. But we couldn't be sure until we actually took the limit. So here I'm going to apply L'Hopital's rule to a case where you need two applications of the rule. So I'm going to start with a form that is infinity over infinity. The limit here is x going to infinity. The numerator would go to infinity. The denominator would go to infinity. So I can apply L'Hopital's rule. Okay, I do that by taking the derivative. So the derivative of, oh, I missed the marker here, sorry. The derivative of x, the derivative of x is 1. Oh, I'm missing things here. The derivative of the natural log of 1 plus 2e to the x, well, the argument of natural log goes in the denominator. 1 plus 2 times e to the x goes in the denominator. Then I have to take the derivative of 1 plus 2 e to the x, which is just 2e to the x. Okay. Now we'll rearrange that and clear off that fraction in the denominator. And we end up with 1 plus 2 times e to the x over 2e to the x. Again, we're still trying to take, this is the derivative now, and we're trying to take the limit as x goes to infinity. And it is okay to rearrange it and do the algebra. That's perfectly fine. Now, again, you will end up with infinity over infinity. All right. So I'm going to repeat the problem right down here. I'm taking the limit as x goes to infinity of this derivative that I got from the first line. They're both going to infinity, so I take the derivatives. The derivative of 2 times e to the x is 2 times e to the x. The derivative of 1 plus 2 times e to the x is 2e to the x. This ends up being 1, and the limit is 1. So the purpose of this was to show you that if you have an indeterminate form, you take those derivatives and you end up with another indeterminate form. It does not always have to be the same as the indeterminate form as the type that you started with, just as long as it's another indeterminate form. Then you can apply L'Hopital's rule a second time. There are other indeterminate forms, and these can be converted into 0 over 0 or infinity over infinity. Here's an indeterminate form of 0 times infinity. If you have an indeterminate form like that, you can convert it by writing it as a fraction. Put the f here and put the 1 over g here, or put g here and put 1 over f here. That way it will either turn into infinity over infinity or 0 over 0. So this other indeterminate form of type 0 times infinity, you do not apply L'Hopital's rule directly. Instead, you convert it to 0 over 0 or infinity over infinity, and then you use L'Hopital's rule. Here's an example. So I'm taking the limit as x goes to 0 from the right. Okay. So what's the limit of the square root of x? It's going to be 0. What's the limit of the natural log of x? Infinity. So the limits would be 0 times infinity. So I don't know what that is, but I can use L'Hopital's rule. So here's what I'm going to do. I'm going to write, I'll put the x in the denominator. So that becomes x to the minus 1/2. I'll leave the natural log of x right here in the numerator. And now what do I have? As x goes to 0, I have infinity over infinity. So I converted it to one of the types that we can use L'Hopital's rule with. I'm going to take the two derivatives. What's a derivative of the numerator? Let me get some of this yellow stuff off of there. The log of x, take its derivative, I get 1 over x. X to the minus 1/2, take the derivative of that, and I get minus 1/2 times x to the minus 3/2. Now let x go to 0. And well, first of all, you could do the arithmetic here. All right, when you work that out, you get minus 2 times x to the 1/2. Now let x go to 0, and the answer is 0. So now the limit is 0. Remember, we're looking for limits, not values. We're looking for limits. But because we're working so much with polynomials and transcendental functions, continuous functions, then we just take the limit as the evaluation. Okay, so in summary for what's going on so far, we have two indeterminate forms, 0 over 0, infinity over infinity. If you have an indeterminate form like that, you can take the limit by taking the limit of the derivatives. Take the derivative of the numerator, take the derivative of the denominator, and then take the limit. Okay. If you end up with yet another indeterminate form, 0 over 0 or infinity over infinity, then you can just repeat the process and apply L'Hopital's rule again. On the other hand, there are different kinds of indeterminate forms, and the one we've shown so far is 0 times infinity. you can take 0 times infinity and turn it into either 0 over 0 or infinity over infinity, and then apply L'Hopital's rule. And remember, once you have taken these derivatives, you can do whatever algebra that's possible. Do that and simplify it, and then try to take the limit again. Here's another indeterminate form. It happens in physics sometimes. Infinity minus infinity. You can't just subtract infinity from infinity. You have to do something proper here. Okay, so now we're going to take the limit of two functions that we're subtracting. All right, but both limits are infinity. According to the limit laws, all I would do is take the limit of f, subtract the limit of g. But then that would end up with infinity minus infinity. So what we do is convert them, try to convert them to one of the indeterminate forms, 0 over 0 or infinity over infinity, then use L'Hopital's rule. Here's this can't always be done, but here, this is a case where it can be done. So I want to take the limit as x goes to infinity of x e to the raised to the 1 over x minus x. Both limits would be infinite. So I write them as some kind of fraction. This works, right? I factored out the x, and then I wrote it as e raised to the 1 over x minus 1 over 1 over x. Now as x goes to infinity, I'm going to end up with 0 over 0. Because 1 over infinity is 0, right? And so if I have e to the 0 is 1, so I'd end up with 0 over 0. I apply L'Hopital's rule. That means I take the derivatives. The derivative of e to the 1 over x is e to the 1 over x times the derivative of 1 over x, and I get that. I take the derivative of 1 over x, and I get minus 1 over x squared. Well, obviously in this particular case, some things cancel. This is going to cancel, and this is going to cancel. And all I'm left with is the limit as x goes to infinity of e raised to the 1 over x. As x goes to infinity, 1 over x goes to 0, e to the 0 is 1. And that's the answer. Actually, there are a whole bunch of indeterminate types. 0 raised to the 0 power, infinity raised to the 0, 1 raised to the infinity. In these types, you use this the idea of the natural logarithm, and you rewrite the equation in a way similar to what was done for rational functions, complicated rational functions, where you took the natural log of both sides, applied the log rules, took derivatives, and then you have to use the exponential to go and get your answer when you're done. It's the same thing here, and I'll give you an example of that. I'll make a comment first. All these examples of some of these indeterminate types, you're going to see them once here. You got to know they exist. Hopefully you'll run into them again, so you get to apply these L'Hopital's rule and get to work with these kind of functions again. But if not, the basic idea you have to remember is the 0 over 0, infinity over infinity. If you have cases of limits like that, use L'Hopital's rule, which means take the two derivatives and then take the limit. So that's the first thing you have to take away from this. Really, you've got to know that. The next thing you have to know is that you can apply L'Hopital's rule more than once, but you can only apply it if the limits are going to be 0 over 0 or infinity over infinity, or you can convert it, the form to that. In other words, I don't expect you to be able to, off the top of your head, figure out what to do with these equations, such as this one right here. Okay, but I'm going to go through for completeness and show you how this is done. So I'm taking the limit as as x goes to 0 of 1 plus x raised to the 1 over x. This would give me the form 1 raised to the infinite power. Well, what is this? Probably 1, but I don't know right now. So what I do is take y equals 1 plus x to the minus x. Take the log of both sides. Log y equals the log of this. Obviously the 1 over x comes out in front, and I have the log of 1 plus x. Okay, so now I say I'm taking the limit of the log of y equals the limit of this side. This side is of the indeterminate type, 0 over 0. So I apply L'Hopital's rule. Right here, I apply L'Hopital's rule by taking the derivative of x and getting a 1. Derivative of the natural log of 1 over x and getting 1 over the natural log of x. Now let x go to 0, and I find out that that's 1. All right. So far, so good, but you're not done yet, because what you have here is the limit of the natural log of y, and you want the limit of y. See, y is equal to this. So you have to take it one more step to unwrap y from the natural log of y. And here's how you do this. You've seen this before. Y is equal to e raised to the natural log of y. So I will rewrite the limit of y is the limit of e raised to the natural log of y. But from the previous page, here's my undo, I know that the limit of the natural log of y was 1 because I just computed it. So this is e to the 1, and the answer is e. All right, let's look back on that again. Okay, what I wanted to do is take the limit as x goes to 0 over 1 plus x raised to the 1 over x power. And I found out with all these gyrations that that limit is e. That is very interesting, isn't it? It's another way to compute e, Euler's number, right? And I did it by saying y equals this, taking the log of both sides, ending up finding out what the limit of the natural log is, the natural log of this form. Then I have to unwrap it by using exponentials, by taking the inverse. Here's another type, infinity raised to the 0 power. What's that? Usually anything to the 0 power is 1. Well, let's find out how this works in this case. Okay, we want the limit. Oops, got the marker here. We want the limit as x goes to infinity of x raised to the 1 over x. As x goes to infinity, 1 over x goes to 0. That's my 0 right here. As x goes to infinity, x goes to infinity. There we go. That's how come I have this form. So we do the same thing. We write y is equal x raised to the 1 over x. Take the natural log of both sides. So I get the natural log of y equals the natural log of x raised to the 1 over x. By the logarithm rules, the 1 over x comes out in front. All right. So I have the limit of both sides. Limit of the log of y equals the limit of this thing. All right. This is going to end up being infinity over infinity, so I have to take derivatives. I take the derivative of the natural log of x and get 1 over x. I take the derivative of x and get 1. Now I let x go to infinity, and I find out the answer is 0. Well, that's good and well, but I've taken the limit of the log. Remember? So now I have to do that other step to get y back. If I know the natural log of y, I know that y is equal e to the natural log of y, because e and natural log are inverses. So this is just a statement that the exponent of e and natural log are inverses. But I can use that because if I'm taking the limit as x goes to 0 plus of y, I'm taking the limit as x goes to 0 from the plus from the right hand side of e raised to the natural log of y. But from back here, I know that that answer is 0. So I end up with e to the 0, and I end up with 1. Okay, if you're still following this, good for you. We're going to have a summary in a minute. This is the last one. 1 raised to infinity. It's a similar process. I'm not going to go through every step. We take the natural log of both sides. You find out you have a type 0, 0. You use L'Hopital's rule. Then you find the limit of the natural log of y equals 4. But you have to get the natural log of y, so you use this idea of e raised to the natural log of y is y itself. So y equals e raised to the natural log of y as x goes to 0 plus. I get it's e to the 4th. Now let's have a summary. Here's a summary. There's indeterminate forms can occur in the case of f over gf times gf minus g and f raised to the power g. There's different types, 0 over 0, infinity over infinity. These are the two that a L'Hopital rule applies, for which L'Hopital rule applies. There are other forms. 0 times infinity, infinity minus infinity, 0 raised to the 0, infinity raised to the 0, 1 raised to the infinity, to infinity. These are all very interesting, especially if you like to play with things, numbers and such. but those are a little more esoteric. I want you to take away the idea that you have this form 0 over 0, infinity over infinity. Know that L'Hopital's rule applies in these cases. And what L'Hopital's rule says is if you are taking the limit of f over g and you end up with 0 over 0 or infinity over infinity, you can evaluate that limit by taking the limit of the derivatives. You can only apply L'Hopital's rule when both f and g are going to 0 or both f and g are going to infinity. Okay? Sometimes those other indeterminate forms can be converted to infinity over infinity or to 0 over 0, in which case you can use L'Hopital's rule. And then remember that you can end up with a situation where you need to apply L'Hopital's rule a second time. But if g goes to 0 and f doesn't, you can't apply L'Hopital's rule. They both have to go to 0 or they both have to go to infinity.